And sorry, Mr. Ouyang. Please turn on your microphone.
Okay. I should unmute myself. Sorry. Thanks, Stephen. And my name is Ouyang from JA Solar, and it's a great honor of mine to share my experience and my colleagues' experience and some insights on technology development. And my presentation will be in 5 parts. The first one is a pivot of modern photovoltaic R&D. When I say pivot, I mean the modern R&D of photovoltaics is significantly different from what we previously experienced before, and I will explain to you why. And then I will go to our module R&D, cell R&D, wafer R&D in a reverse order, interestingly, and then I will make a conclusion on my presentation. The first part. There's many predictions on the market of PV industry development, but I always would like to use the ones that given by scientists and engineers, because we are scientists and engineers. Unlike the ones given by market predictors, we look into the future in a brighter way, because we believe if we want to overcome the whatever 1.5 temperature C global warming issue, there's a certain target we have to challenge and we have to achieve. So there's not much, maybe there's a big year or small year, there's a fluctuation up and down on the market, but we believe overall it's going to be big. And on the left-hand side, we publication published by Science in 2023, and on the right-hand side is IEA in 2023 as well. The key messages I wanted to give was that there shouldn't be any problem in the next 10 years to have a 25% annual growth rate. And by 2030, we should be able to get 600 gigawatt plus new installation. And in terms of the size, accumulated installation has achieved 1 terawatt, a milestone in 2022. And it is predicted to be like 5 terawatt in 2030 when saturated. And it's debatable whether it will actually be saturated over there or not. But anyway, if it is saturated, then the replacement will be more than 3 terawatts per year, which is quite significant. That means when we think about what new technologies we need for the industry, we must be thinking of a few things. Number one is we have to be able to support mass scale production. We face challenges on material scarcity, equipment availability, and different application scenarios. We have to tackle these challenges. And then we have to be very cost effective on materials and land in use. And we have to make sure our PV product is really reliable in order to delay the solar module replacement for a full life cycle management. So these are the 3 key areas I think that's going to be important for the development of new technologies. And then the great pivot is, in my opinion, from watt peak to kilowatt hour. Conventionally, when we say PV R&D, we always focus on nameplate, power rating, and efficiency. But then when we have larger penetration of renewable energy on the market, we realize that effective modern PV R&D will have to focus on creating different values for customers, and extends the scope to lower LCOE, customization, and eventually ESG. So the difference I put in a chart here for comparison. When we talk about high power, nameplate power, we usually think of, we want to make the solar module larger, and with the high cell efficiencies, and low cost means why don't we use cheaper boom of materials, right? But the modern R&D, we focus on in-field high power with best LCOE. That means it's not only about, but moreover, it's about we have to make sure it's a full day, full season, and all scenario superior power generation. Customization means maybe some customers think, well, LCOE is important, but if my module, my project is in a dusty area, then self-cleaning, that's a critical characteristics of the product. That's what we look into in JA. I'm pretty sure in our other PV manufacturers as well. And if the project is near the airport, for example, then there's a requirement on anti-glare effects. And some for aesthetic reasons, people may like full black or colorful PV. And when it is close to the coastal area, then we need to think about reliability in marine applications. And then it's a reliability and robustness. So that means we want to product something that with ever lower degradation in extended product lifespan. And also it has to be very tolerant to extreme weathers like hailstorm and winds, stuff like that. And the last but not least, we have to think about the ESG. In manufacturing, we want to have low carbon footprint in manufacturing, which means the material in use, the wafer thickness, and whether we can use a low temperature process to replace the high temperature process, stuff like that. And when we design a module, we want to make sure at the end of the life of the solar module, the panels will be easy to recycle. So there's a lot of more stuff to research and development in this industry. Then interestingly, in my opinion, and a lot of researchers, specialists agree with me that we have to design R&D in a reverse order. Conventionally, we think, oh, we want to have a good silicon wafer, then cell, then module and system. But in my opinion, it should be done in a reverse module. Let me explain to you. So the overall target, people buy solar panels, they want to build an effective PV system. That means we want to design for low LCOE. We have to be able to customize for different scenarios. And the modules and the PV system will have to be optimized for inverter and grid connection conditions. That give us requirements and on the solar module selection. So in order to achieve the requirements on the solar PV system, we want to optimize the module size and mounting, and we want to choose reliable bill of material, and we have to carefully design the cell outlet and the interconnection. And then we have to customize for different working scenarios. Then that's the requirement on a solar module design. Then in order to achieve this solar module design, and we have to think about what solar cells we want to produce. Then we think, okay, we need to have high efficiency solar cell with low CDM loss. And we want to make the solar cell be able to present low degradation on LID, PID, etc. Then I put down the requirement of the solar wafer to optimize to achieve these high efficiency solar cells with low degradation. So actually now in JA Solar, our research in a reverse order, that's what I mean. LCOE, I don't need to explain too much about that. That's the levelized cost of electricity, more important than nameplate power, more and more important. And on the right-hand side, on the left-hand side, you will see the PV module takes a big part of the cost structure, which means the better solar module we produce, the better LCOE we will have for the solar farm. And on the right-hand side, you will see that in order to achieve these, we have to have low BOS, balance of system costs, low costs, and high power generation capacity and long-term reliability. That put on the requirement on our solar module R&D. Then I would like to make our latest product, most advanced product, DeepBlue 4.0 Pro as an example. We have very important features built in this design, like SMBB, like 16 BB or even 20 BB, that will minimize the power, the light reflection on the front surface, and will minimize the electrical loss when doing interconnection. That isn't one important design. And also we designed rectangular wafers with the thinner wafers, 125 micron. That means we, without changing all of the width, no problem with handling, we can have variable length to fit in different applications. And with the high density encapsulation, that means we can put more solar cells in a solar panel, which will make sure we have high power output. And last but not the least, we want to have highly reliable encapsulation materials to make sure that our solar modules can survive in a field for a very long time. So then probably number one important feature other than the power rating is the low degradation. So compare with the P-type counterparty bifacial modules, our modules, N-type modules are significantly better with less than 1% first year degradation. That means we have very good control on LID, LETID, stuff like that. And also annual degradation is much less than 0.4% annual degradation over the 30 years. That means when you build a solar farm, when you purchase a module, this module can generate more power in a much longer time. And one thing I want to highlight is the temperature coefficients. So our module has a very low temperature coefficient. We know it's like people, right? And any materials will age quickly at high temperature. That's the chemistry and the physics behind it. Roughly, if we have 10 degrees of higher temperature on a module, then the degradation mechanism will accelerate by 1 order, which is quite significant. When we design a module, when the module can be at a lower temperature in high temperature environment, that means we can generate more power, and also the module will last much longer in a much better condition. Then on the right-hand side, you will see two comparative charts between the N-type modules and P-type modules. Then the dark blue is the light blue is the N-type one. Under the same environmental condition, and the module temperature is much lower, which is also very important. I mean, these things is not necessarily reflected in the nameplate power rating, but is significantly important for the power generation over time. And one thing I want to emphasize is bifacial ratio up to 80%. That's very high. It's almost like you have freebie from the reflection at the back. It's like a free gift you have when you put the solar panel on the roof. Of course, it depends on the ground reflectivity, but also on the high-low latitudes. And in the high latitudes, you have more reflection at the back. But overall, we see quite significant benefits from the rear reflection with the design with the bifacial design. And then in order to achieve this, of course, we ask ourselves what's best the solar cell technologies we have to put on in order to make it happen. And this is a chart, little research I did, and I would always like to show you too. It's an interesting story. A little research I did was I compared the PERC market prediction given by ITRPV, International Technology Roadmap of Photovoltaics. That's a very dominating and a roadmap organization and organized, contributed by all the tier 1 manufacturers and major research institutes globally, then the dot line is the prediction in each year. If we look at the bottom one, in 2015, all the experts said by 2019, the PERC technology will achieve 25% market share. And in 2016, people find we underestimated the dominance of the growth rate of PERC technology, and the experts exchanged the prediction to say, okay, by 2019, maybe the market share will be 32%. And it's kind of iteration and then 35%. And in 2018, so no, we significantly underestimated, and the next year will be 50%. But actually, when in 2019, it's 60% market the reality. What I want to say was the key message I want to give is that the market adoption of critical cell technology are almost always being underestimated, even by the experts. So that's really the power of new technology, how they can change the PV market. People always think, oh, technology is important, but actually technology is more important than you think. Then I want to share a little bit on a journey of our solar cell R&D of JA Solar. And our journey in 2007 started with aluminum back surface fuel cell. And you see that with the new technologies, it's very nice straight line over there. And the dot one is the one in our R&D lab. And the solid line is the one that in a mass production in the market. So you will see that if we take the triangle, for example, the hollow triangle means the PERC cell that we put in R&D back in 2009. And in 2014, we started putting the mass production. And by the time we are actually the first one in the world to produce bifacial PERC modules. And we are one of the first ones to have selective emitter technology implemented in it. And we are also the first one to have gallium doped in an N-type wafer to minimize the light-induced degradation. And you see, interestingly, roughly it takes 5 or 6 years, let's say 5 years, before we have our, that is a gap between the start of our R&D and the start of mass production. So 5 or 6 years, that's the time we need to make something happen. Maybe you think of some companies, a bit more aggressive companies, they only put like 2 years in R&D, then they rush to put in the market. But we believe probably 5 years, that's the right timing. If you really want to be responsible for your product, that means you test it a lot and do a lot of reliability tests, and you do a lot of development. That's roughly 5 times. That's the time we have to invest for R&D. Then you, in the beginning it's PERC, then we have TOPCon and HJT, then now it's XBC and the tandem structures with higher and higher efficiency. So the idea is that R&D always have to kick in years ahead, waiting for the call or sometimes no call from the market at the right time. So we always prepare something when the market, when our customers need new products, we will have our product ready to be mass produced. So that's the idea behind it. So this slide is a little bit more technical, just to give you an idea of what do we do and how we make the best solar cells. And here I take the TOPCon solar cells, for example. On the left-hand side, what we usually do is to analyze the lost mechanisms, why we can't achieve the theoretical limits of a solar cell with a certain structure. We will have like the lost we categorize into different levels like optical losses, electrical losses, surface recombination, and current transportation, whatever, there's a lot of things. And we do a lot of iteration. You can see from Bycium 2.0 to 3.0, 4.0 and 5.0, we try to minimize the loss and push towards the theoretical limit. And on the right-hand side, we want to, this is the spectrum. We want to make most use of the solar, the sunlight shining on the solar cells by squeezing, by making most use of the light. And on the left bottom, that shows how we minimize the surface recombination and reduce the bulk recombination in order to achieve the target we want. So the conclusion was we have to continuously do R&D to minimize losses and enhancing light utilization, such as period mid optimization, refined metallization SE, boron diffusion, and fine-tuned passivation, etc. So what I'm saying was our customers, they not necessarily need to understand everything behind it, but we in our R&D department, or not only just in JA, right, in overall all the big manufacturers, we try very hard to achieve these kind of good results. So with the mechanism and the mindset in our mind, this is an example of the achievement. What we do. This is a TOPCon cell efficiency and PV trained chart here, and you can see it's going on all the way. But maybe we have up and down a little bit fluctuation, but overall, the trend is we always achieve very high higher and higher efficiency on the way with higher and higher VOC on the way. So that's what we do behind it. So as a result, so this is our latest Bycium cells technology in mass production. When we transfer from the R&D to mass production, we achieve a 26.4% efficiency with high VOC open circuit voltage as high as 740 millivolts, with a lot of fancy technologies on it, on the front surface, in the middle, at the back, a lot of stuff. I don't want to go to too much details, but there's a lot of things like you can say JA inside. There's a core of what we see on a module. Then we look back into silicon R&D. Particularly when I say bulk recombination, if you remember in the previous slides, that very much dependent on very good silicon we have as a beginning. And actually, this is one of the biggest benefits of JA Solar as a fully integrated solution provider along the way, because we can have a full supply chain optimization and R&D from the wafer, actually ingot pulling all the way down to modules and system. So this, I give you some example how we achieve higher crystalline silicon quality by reducing oxygen contents, ppm. I think it's as low as lower than 10 at this moment in order to achieve high quality wafer. We, in the last 14 years, by implementing advanced technologies, we reduced the oxygen contents by 42%, which is a big milestone, and it's really, really a great foundation for high efficiency cell and module and effective system on the way. And also we also not us, again, not only us, the whole industry moving into larger size wafers in order to increase the yield of the ingots from probably, from the beginning 125 mil all the way down to 182 up there. And now we believe rectangular wafers are the way to go. And by doing so, the monthly unit yield increased by 510% in the last 14 years. And the third one is that we keep putting innovation in our manufacturing processing and equipment. By doing so, we significantly reduce the cost of the wafer. We introduced the new pooling method, diamond wiring method, and continuous pooling furnace, and intelligent factory, and thinner wafers, and with the utilization of the edge. So also by doing so, we reduce the cost of wafer by almost one order. That is play a significant role into the fact that now we can have such cheap solar modules in the market to be used by the homes and utility. So all the R&D efforts are put together for better future of our planet. So by 2023 of Q3, JA Solar accumulatively shipped modules for 166 gigawatts, which equivalent to annual electricity production of almost 216 billion kilowatt hour, which was equivalent to planting 11.6 billion trees and reduction of CO2 emission of 216 million tons. So JA, together with all other R&D colleagues in the world, in the factory, in the research facility, we all work out together very hard to make our planet a better place to live. So that's the end of my presentation. Hope you enjoyed it. I give back to you, Stephen.